Okay, we'll go ahead and we'll get started here. So I appreciate you all making it in for, this evening's meeting. It's obviously it was a busy day here in North Texas, so confirmed already 6 tornadoes in the area, and potentially another 6 more could be added on top of that. We'll just see what the surveys say. Which, given the events of all the tornadic activity in the DFW area this morning, it leads to a nice segue to our guest speaker for this evening for our December meeting. So I like to introduce everyone to Dr. Harold Brooks. He is a research meteorologist and a senior scientist at the National Severe Storms Laboratory. He has degrees in physics, mathematics from William Jewell College, and then master's in atmospheric sciences from Columbia University, and then a PhD in atmospheric sciences from University of Illinois in Urbana-Champaign. He was a research associate with the National Research Council, and that has been part of the National Severe Storms Lab since 1992. Among many of the things Dr. Brooks has done and all his accolades, he's authored 2 climate assessment reports. He's been part of the climate change science program. He's organized Weather Ready Nation workshops. He's obviously done a lot of work with severe weather, which is, again, very timely with what has happened this morning here. And his work is well known in the community, both in the country and internationally. He's been awarded the Department of Commerce Silver Medal in 2002, the NOAA Administrator Award in 2007, awards for outstanding science contributions in 2012, Distinguished Career Award in NOAA in 2021. He's also an award winner across the pond in Europe as well. So without further ado, I give you Dr. Harold Brooks, and he'll be talking about tornado warning performance. Dr. Brooks,
Thanks.
It's all yours.
Thank you very much. And I thought briefly about looking at the warnings that came out today and trying to do something with them, but decided that didn't seem quite I'd be able to do very much with them. But I've spent off and on over the last 20 years. I've spent time thinking about the state of the tornado warnings, and essentially trying to look at them in bulk as a system, rather than necessarily, while it's important to think about perhaps the process and the evidence we use to make decisions. I've spent a lot more time thinking about, well, what is the performance if we look at the statistics of all of the warnings? What do they actually tell us about the culture, or how we actually behave? And every once in a while, people get a little worked up that I say things that they think somebody may be offended. So I have a standard disclaimer to go through, that this is all mine. Don't blame anybody else if you don't like anything I say. It isn't my thing. For those of you who can read quickly, this actually does have a large chunk of the intro to Monty Python and the Holy Grail, in Icelandic even. So take care of that. Yeah, this is like I stole things. Okay, so let's just do a little bit of just background. I'm going to talk today about both the changes in performance over time, and then actually what happens during time as we put out warnings. And just as things that we want to make sure everybody knows, the duration of tornado warnings, valid time should be 15 to 45 minutes from issuance. For tornado expected to continue beyond the valid time of the original warning, a new warning should be issued. All warnings end at multiples of 15 after the hour. That's been true. The last time one did not end at 15 after the hour was in 2015. And the last time one didn't end at a multiple of 5 was 2005. So essentially, forecasters can choose the initial length of the warning, 15, 30, 45, or 60 minutes. There are actually several other times, but because we round to 15, you only need 4 of them. And then the software rounds to end at the multiple of 15 after the hour. So if you put out a warning, a 30-minute initial warning that was issued at 8:07, it would end at 8:30 because it would get rounded down. If you waited one more minute and issued it at 8:08, it would end at 8:45. And if you look back at the directive, all of the 60-minute initial times and half of the 45-minute ones, the ones that get rounded to be longer, are in conflict with the directive. And that's just, that'll be one of the curious results, is that the directive doesn't seem to matter very much to things. So, but I want to think about warnings as a problem decision theory. There's uncertainty, there's time pressure to put them out, and there are asymmetric penalties typically for, we don't think of a false alarm or a missed event as being the same thing. And this is true in a number of other decision-making contexts. I'm a collegiate volleyball official, and we essentially have the same thing. We can, there's sometimes when we have to make calls that are not, it's not completely clear what the correct call should be. And we can't sit there and wait a long time to make that decision. And there may in fact be, penalties that are different for either calling something that didn't happen or not calling something that did happen. So to do this as a real simple model, imagine some variable, and it may be a very complicated variable, maybe a collection of a whole bunch of other observational things or other things that are going on in the tornado world. It might be what does the radar look like? What does the environment look like? And it provides some weight for something to be true. And we have a distribution of that variable for both the yes events and the no events. A real simple example that many of us have encountered at some point in our lives is a white blood cell count infection. Typically, people who have suffer from certain kinds of infections, your white blood cell count will be elevated, and people without infections, white blood cell counts will be lower. But that's not a hard and fast. If your number is above 702, you've got an infection, and below you don't. We know that there are people whose white blood cell counts don't get particularly high even when they are infected, and people whose white blood cell counts are higher than others even when they don't have anything. But yeah, if you were to have some event occur that required you to go into an emergency room this evening and they did a blood test, that would be one of the first things they would look at, and they would basically make a part of their determination of whether you had an infection or not would be based on how large that number is. We want to focus also on non-trivial problems. When we think about the tornado warning problem, we're not going to think about, we want to think about things like any of the storms that any of the forecast offices in the region saw this morning. They had to think about whether they were going to put a warning out or not, for a tornado warning out or not. Whereas a radar echo, say the middle of next week in the plains when it's below zero, it's unlikely we really want to give them a whole lot of credit for getting that forecast right. So we can think of as a model of this, and I'm going to model this as Gaussians, but that turns out that doesn't really matter. What we really care about is the difference in the cumulative distribution functions, but looking at as a problem in Gaussians makes some of the math a little bit easier down the road. And so we might see here this is some sort of a weight of evidence going from left to right, and that in general the yes population is a little bit higher than the no population. This was a model I first wrote up in 2004, and then we have to maybe we have some uncertainty, and that at the various values along the way, you could say that we have to decide at some point, perhaps in the warning situation, say we're going to call it a yes when it reaches a certain value, and say this horizontal. I put a line here on the vertical axis here, on the horizontal axis here, where I basically said I'm going to call anything that's to the right of this a yes, anything below this to the left of this as a no, and in this case, I'm getting almost all of the yes events. I've got a few I'm missing. I'm getting them. I'm getting almost all of them, but I have a lot of false alarms. The area to the right under the blue, and we actually can come up with. You'll see in a minute the 2x2 contingency table. This division helps us then basically break it down into a yes/no event and a yes/no forecast or identification. Well, if I don't like false alarms, I could put my I could put it over here. I could put the barrier over here, and now I'm only getting some of the warnings or some of the events to be called a yes, but I have very few false alarms. If I'm agnostic about what the errors are, and I think the errors are equal, I might put it right in the middle. And again, I can have this occur, and I can break things down however I want to. And as I slide that line of back and forth, I'm basically trading off between false alarms and missed events. The difference in these two things, between these two, is D prime. Between this can be as a measure we can get out of this is a difference between where the two peaks are. In this case, these are the D prime is set to be one. These both have the same standard deviation, and so this is one standard deviation apart. And it turns out when we actually ask people about is a system working well for identifying things, this is roughly where human beings start to think the two things are different, is one standard deviation apart. And you can think of this D prime value as a measure of science and technology, and where we put the vertical axis, or where we put the vertical line, is strictly a function of how we value the different kinds of errors. We can also look at this if we have a rare event. So yes events are uncommon in this case. I still have the same D prime. It's the difference between where the two peaks are. But now I've made it to where this is much like the tornado problem, in which the tornado warnings, even tornadoes, even out of severe thunderstorms, are not all that common. And now what happens is if I move my the line a little bit, I can actually move the fraction of the yes events that I correctly identify as yes. I can move it a lot without moving the number of false alarms I have. And this turns out to be one of the problems that we face in the tornado warning issue, is that with our current state of our science, our warnings are our performance metrics are relatively insensitive to false alarms, and much more sensitive to changes in probability detection. And we'll see that in just a minute. And we can take that into a 2x2 table for the quality of the forecast. We can basically write down where we have yes events. We have events that are yes, and forecasts that are yes or no. And we have these four elements, and we can come up with a probability detection, which is basically the fraction of the events that are forecast or warned on in advance. A probability of false detection. So for no events, what fraction of them had a yes forecast associated with them? Something we call a success ratio, which is 1 minus the false alarm ratio, which is the success ratio is the fraction of the forecast yes events which actually had something happen with them. When we forecast a yes that the event actually occurred, we can come up with all kinds of other quantities out of this. And there's a parallel table to this that looks at value. Do you take action to protect yourself? And because this is also another part of the decision process, is if a forecast is issued, do I take action? If there's a probability of an event occurring, at what probability do I actually protect myself against it? We have a similar looking table, and the big quantity we can get out of this is something called the misclassification cost ratio. And it says that a person who is attempting to minimize their losses will take action if the probability of the event is such that it's the cost of the false alarm divided by the sum of the cost of false alarm and the cost of missed events. So that if you think that false alarms are really important and they're very costly to you, you will want to wait till this value is higher, and so you'll require a higher probability of the event occurring. If false alarms are cheap, you tend to protect almost all the time, and so you protect at a much lower value. And we could draw a real simple diagram of when I showed you the two Gaussians. I can draw this real simple diagram that now plots the probability of detection versus the probability of false detection. And this is what this curve looks like. There's a point where we never make the forecast, and so we never get anything, but we also never have a false alarm. And then up in here in the upper right-hand corner, we're always getting all the events right, but we have a lot of false alarms. And the area under the curve here, under this curve, or it's frequently called AWK, it turns out to be a statistical measure that tells us how likely it is if I randomly put one value from the yes distribution and one value from the no distribution, what's the probability that the yes distribution value would be higher than the no distribution value? So we obviously want that to be larger. And so now I've taken a case now, the red arrow is showing where I never forecast the event to, or I always forecast the event to occur. Over here, I never forecast the event. And in here somewhere, this is sort of like current tornado practice. And where as this red line, as I move the red line along, that's essentially can be described by a value of that misclassification cost ratio, alpha. Moving towards the bottom left means that people are much more sensitive to false alarms. I can also draw this on what we call a performance diagram, the probability of detection versus the success ratio, or one minus the false alarm ratio. And this curve is the identical curve except transformed. Perfect forecaster up here in the upper right-hand corner. And we can see that as we go along with keeping constant quality and just changing our threshold for when we decide to put the warning out, we move down from high POD, low success ratio down to high success ratio, low POD. And it's similar kind of a thing when I change the thresholds. So the fundamental question is, what is actually an event? What are we going to call as a yes event? And for this, we're going to call it a tornado occurring, perhaps. What's the correct forecast of an event? Is something else we have to think about. And what's a correct null? So again, we come back to the fact that I don't want to give you too much credit for making the really easy forecast, the middle of January below zero. I didn't put a tornado warning out today. I don't really want to give you much credit for that. And so as a crude estimate, it turns out that for when we look at this tornado warning versus severe thunderstorm warning, roughly about 10% of the time that decisions are having to be made that are relatively challenging, a tornado actually occurs. That's not an exact number, but it's certainly not 0.2 and it's not 0.05. Another big question, what's the lead time for an event that's not forecast in advance? Officially, according to the National Weather Service, it's 0, but that leads to a lot of confusion with the probability of detection. And it's a lot cleaner to separate out warned in advance storms or tornadoes than from other tornadoes. So officially definitions, back in the county-based era, back through September of 2007, the false alarm ratio was warnings without tornadoes divided by the total warnings. The official POD in that 2x2 table, the A quantity in that 2x2 table I showed earlier, is if we put the warning out before the tornado or during the tornado's existence. And since the official lead time for an unwarned or warned during a tornado is 0, that means that the official lead time definition in the county-based area was actually what was the lead time for tornadoes warned in advance times the probability that we actually warned in advance. And when we look, and in the storm-based area, the definitions got changed, false alarm ratio stayed the same. But actually what's done now is that the tornadoes are broken down into 1-minute segments. And for each tornado, we calculate the percent of the event warned. And the mean lead time, again, counting unwarned segments, is 0. And for groups of warnings, we take the means of those quantities. And it turns out when you look at this, that means that we put a lot of emphasis on short-lived, usually weak tornadoes. So that if you miss a 1-minute long tornado, that will hurt your metrics a whole lot worse than missing 10 minutes of a 20-minute long tornado. And since the longer lasting tornadoes tend to be stronger, that means we care a lot more officially about weak tornadoes. And in fact, if you wanted to get to, say, a 70% probability of detection, you have to get at least 67% of the F0 and F1 tornadoes warned in advance, or you just can't make the metric. There aren't enough of the stronger tornadoes. The data I'm going to use are from verification.nws.noaa.gov. I've tried to correct some obvious errors. There's a 49 million square mile warning in the database. I gave it its correct area, which was 270 square miles. If you're not able to figure out 49 million square miles very quickly, that's basically the area of the Atlantic Ocean. And there's nothing obviously wrong in the warning text. The points close. I don't know why they came with 49 million instead of 270. So when were tornadoes warned on? And this is looking annually, 1986 when the database begins, up through 2021. where the fraction that we're warned in advance is the red, during is the gray, and the blue is never warned on at all. And back in the late 1980s, we warned about 25%. About 25% of the tornadoes warned in advance. That number grew to about 70%. In 2003, it was kind of flat, and then you see that it drops after 2011, 2012 to where now we warn a little bit over 50% of the time. 50% of tornadoes are warned on in advance, and we see a mirror image of that when we look at the never warned on. The warned during has gone up from about 8% of tornadoes to where now it's about 12% of tornadoes are warned on during the tornado. If we then look at what the lead time, the different ways we could think about lead time, if we take the average, if we take the mean of tornadoes warned in advance for each year, that number was roughly 18 and a half minutes from the late 1980s up through 2011. And now that's dropped starting in 2012, 2013 down to about 15 minutes. The official definition from the county-based areas, we can still apply to the current, shows a long increase and then flat, and then again back down flatter again. And you'll note that this is basically this is a scaled version of the fraction of the tornadoes warned on in advance in the red, multiplied by 18 and a half minutes, and now by 15 minutes in the last decade. And so actually there's a lot of confusion that the official definition the official storm era number runs around 8 to 10 minutes in advance, but it's in reality that's because a lot of half the tornadoes we don't warn on in advance. And if we just look at what's the warning, what's the lead time if we do put out a warning before the tornado, it's about 15 minutes right now. Different ways to calculate the probability of detection. I won't go into this a whole lot of the fact that it went up from that 25 to the way that works. I think the best is if we did we warn in advance, and that's where we go from 25 to about 70, and now it's about a little over 50%. The false alarm ratio didn't change very much, and we can actually plot now the POD versus the success ratio, and I've color coded these by different eras. So remember again, the success ratio is 1 minus the FAR, and you'll see that over the grays are prior to 1995, and if we look actually after starting in 1990, there's since then, out of the 32 years in the database since then, 29 of them are in about a 7 to 8% window. And so the false alarm rate, while the PODs change, has varied from 70 to 35%. The FAR just hasn't moved very much. The best it's ever been is about the best the success ratio has ever been is about 30.32, which is 0.68 for the false alarm ratio, and the worst it's ever been has been just a little bit worse than. A little bit better than 0.2, or the false alarm ratio being a little bit less than 0.8. So we have a lot more variability in false alarm ratio in POD than we do in false alarm ratio. And what we see as we look through time is the POD goes up through into the early 2000s without much of a change in the POD in the false alarm ratio. The early part of the storm-based warning, the red dots are pretty much identical to where the late part of the county-based warnings are. And then we see that this dot is 2012, and the 2013 are down here, and they're pretty much having the same. The curved lines are critical success index, a crude metric for skill, and we kept basically the same CSI all the way through, and we've dropped the POD, and in exchange for getting a little bit better false alarm ratio. And the POD basically dropped by about 16 points, and the false alarm ratio dropped by about 5 points. And we show the same thing on the relative operating characteristics curve. That's a diagnostic that's used in a lot of different fields. It's the same kind of a thing. This line, the middle green line is the D prime of 1. So our warning quality is basically between 1 and 1.5. And again, we see improvement in getting to higher values of D primes. We're able to discriminate between tornadoes and no tornadoes a lot better as we go from starting in the late 1990s, early 2000s. And this is likely to be a result of the results of Vortex 2 coming in, the Warning Decision Training Branch doing their work, more experience with the Doppler radars. And then since then, starting in 2012, we see the decrease down to lower values of the POD. But that our ability to discriminate has stayed the same. And I mentioned that that we can think about this as what is the D prime value, and then what is that misclassification cost ratio alpha. And we see it's a similar kind of a picture. You can see where our D primes are 0.1. Up says that false alarms are much more costly. And what you see in this is we can interpret this as if we ignore the 1980s data that we just weren't very good. Since then, what you see is between the early 1990s and the late 1990s, the quality didn't change. The D prime stayed the same, but we started acting like false alarms weren't as costly, and that was in large part it became software made it easier to write the warnings, and so people put more warnings out. And then we moved into the early 2000s and increased our quality. So we were able to discriminate again between tornadic and non-tornadic better. And then starting in 2012 and to 2013, we moved up, acting like false alarms were more costly again. And this is roughly the change from the early part of the storm era to the 2012 to 2011 is essentially equivalent to thinking, we suddenly started thinking that false alarms are 50% more costly than they used to be, than we used to think they were. I want to move on to look at some of the effects of the rounding and what we do with the warnings and how that relates to policy. And so if we issue longer duration warnings, longer duration tend to be larger area. They increase the mean lead time, our performance diagram quantities. That'll mean we decrease the false alarm ratio, increasing the SR success ratio, and it increases the POD. This is orthogonal to the change in the decision threshold, so we can see when these things happen differently. It's hard to empirically measure the POD change, so we'll look at the FAR change as we make longer warnings. We'll only look at the last 10 years, 2012 to 2021. Central region began a big emphasis on reducing false alarms in 2012. And a lot of offices in Southern region started in 2013. Not all, but many did. And the default warning length in the software system changed from 45 minutes to 30 minutes in 2012. No one seems to know who made that decision. It's likely it was just the software person coding it up who read the directive and knew that if the 30 minutes was the default warning, that it would be inside of that 15 to 45 minute recommendation, or 15 to 45 minute time from the directive. But that happened, and the effect is clear what went on. So let's look now at the false alarm ratio by duration and by the rounding time. And so the black squares are the overall warning for 60-minute long, for 15-minute long warnings at the top, 30-minute, 45-minute, 60-minute. And so if you use for every one of those time increments that a forecast office uses, it roughly gets them 5 to 6 points in FAR. And remember that overall, our range, if you get the interannual variability, the entire range from the early 1990s to now has been roughly 8 points. So this is almost giving you as much of an effect as our best and worst years, just by going from 15 to 30 minutes or 30 to 45. If we go all the way down from the 15-minute warnings to the 60-minute long warnings, that's actually 16 points of improvement in your false alarm ratio just by using longer warnings. Going from left to right is actually the is, did you issue the warning at, say, 7 minutes after the hour versus 8 minutes after the hour? And so this is now, the ones on the left side would be 7 minutes after, or 8 minutes after the hour, so that you get longer. I'm sorry, the other way around. This is 7 minutes after the hour, so this is now, you get a shorter warning because you issued it because the rounding decreases it. And on the right-hand side is now you issued it at 8 minutes after the hour. And what we see is that basically, again, if you issue a warning at 8 minutes after the hour or 23 minutes after the hour, as opposed to 7 minutes or 22 minutes after the hour, your false alarm ratio drops by about 5 to 6 points. And so again, waiting one more minute for office waiting one more minute to issue the warning would actually improve their statistics by as much as our best to worst year almost. And so it turns out there are offices that use a whole lot of different strategies. There isn't, I can't really see much that says people are waiting an extra minute, but we can see real big differences in how things work when we issue the 15, 30, 45 to 60 minutes. And so actually, if we look at the POD, this is now looking at the 72 stations that issued 100 warnings in from 2012 to 2021, and the mean warning duration from each one of those offices and their POD. There are some real outliers. I don't remember which office this is, but they have a really low POD. But the POD basically, as you go from the shortest warning offices up to the longest warning offices, so the offices that are basically issuing 30-minute warnings most of the time to the offices that are issuing 60-minute warnings most of the time, their POD goes from 0.4 up to about 0.7. And so again, this is now the whole history of the warning process changes, going from a 30-minute warning to a 60-minute warning. If we look at the success ratio, so 1 minus the false alarm ratio, a little bit, it's not quite as strong of a signal, but again, it probably gives you about 20 points in FAR or success ratio by issuing really long warnings. And so the offices that issue the 60-minute long warnings tend to outperform offices that issue 30-minute warnings pretty substantially. And we can see this now. This is now, I've taken I said there were 72 offices. And I've taken them by the 18 longest offices, and then the next 18, the next 18, and the next 18. And so the 18 offices that issued the longest warnings, their mean warning length was 41 minutes. And their warnings are 361 square miles. The shortest warning office is about 30 minutes and 260 miles. The blue is the annual numbers. And what we see is that as you go from the shortest warning offices to the longest warning offices, it's more than the difference in the annual performance. And again, this is orthogonal to what a change in decision threshold would be, which would be we kind of be coming along those curved lines. And so the longest issue, the offices that put out the longest warnings average whatever, almost 20 points higher POD and 10 points lower FAR, higher success ratio. Oops, oh my gosh, oh my gosh, I lost a slide. That's not good. Oh, well. So I'll just talk about it then for a second. I think one of the things that we deal with, one of the analogies I have for this is, is anybody out in the audience familiar with the name Fred Merkel? Anyone heard of him? He was a pretty good baseball player. Played for almost 20 years. Was a real good dead ball hitter. He is most known for one play that he made when he was a rookie. The Giants and Cubs were tied for first place in 1908, and Fred Merkel was on first base. Somebody else was on third base. 2 outs in the 9th inning at Polo Grounds in a tie game. A single into the outfield, and in those days they actually put people out behind ropes in the outfield when the crowd was really large. Ball goes out into the crowd, run scores. Fred Merkel never goes to second base. and is called out for not going to second base. Game is declared a tie, replayed, the Cubs win. The replay win the National League pennant and go on and win their last World Series before 2016. And it's known as Merkel's boner because he didn't go to second base on a single. It turns out that Fred Merkel did exactly what every baseball player had done for 30 years. Nobody went to second base in that situation. And the only reason it got caught that time was that the play had occurred 3 weeks before with the same umpire. They only had one umpire at the time, with the same umpire at the Cubs playing against the Pirates. And the Pirates had complained, and they had said, shouldn't he be out? And the umpire said, I wasn't watching to see if he actually touched second base, because they didn't do that because no one actually expected that. And the Cubs pointed out, well, again, according to the rules, he should be out. And in Pittsburgh, they didn't get the call. They have him again, and in the ninth inning, when they get 2 outs and a man on first and third, they point out to him they're in that exact same situation. And so that time he watched and he enforced the rule. One of the real questions I have is that Major League Baseball faced a dilemma. They could either decide we're going to enforce the rule the way it's written in the rule book, or we can rewrite the rule book to codify the behavior that people have been doing for the last 32 years. And they chose to enforce the rule. And so now no one ever thinks about not going to second base in that situation. Well, I think Weather Service faces a similar problem right now. We have there are offices that more than half of their warnings are outside of the duration that the directive says they're supposed to be. And I have no idea that their performance is better by all the metrics we have. And I think Weather Service has to make a decision at some point. Do we enforce the policy, or do we change the policy to reflect what people's behavior are? I mean, currently the directive, because of the directive, the 15 to 45 minute time on the directive, it predates the reround all of the warnings to end a quarter after the hour. And as a result, the software actually now, because the software does this rounding, the software forces a lot of warnings out of the directive that were originally intended to be in sync with the directive. And so we've actually reached the point that the software itself violates the directive, the warning software. And that is a problem, because I can imagine a situation in which somebody has a really long lead time warning on a warning which is longer than what the directive says it should be, and bad things happen. I mean, a lot of this stuff is completely outside of our control. And if that happens, some journalist or congressperson could say, did the bad thing happen because this warning was outside of the directive, was outside of policy? Why do you have a policy if you aren't going to enforce it? And I think that's really one of the things. The National Weather Service needs to decide what it's going to do with the Fred Merkel offices, and whether it's going to say we like Fred, and Fred's our hero, and we're going to make everybody, we want everybody to be like Fred, or we want people to do what we wrote years ago. And I think that's a real challenge for them. So our bottom line is that what we've seen is that we saw a big change in 2013 associated with the increase in false alarm, emphasis on false alarms. A big decrease in the POD, some of a decrease in the false alarm ratio, but smaller, which was predictable because of the nature of the problem. But we also now know that the really long duration warnings provide much higher values of POD and much lower values of FAR than the warnings that are in the directive. And it's larger than the historical range of annual performance. So I'll close with that. And we can talk about whatever we want to, and find out how people's days were.
Dr. Brooks, thank you so much. That was an amazing talk. We appreciate you taking the time to do that. So we'll go ahead and we'll open the floor up to questions here in the room or online. Yeah,
I have a question. Have you looked at the warnings in a rural environment versus urban environment. And I wonder if those false alarm rates go up in an urban environment.
Oh, yeah.
Maybe more risk.
There, I have not done it. We've done some work with there's been more work done with distance to the radar. There's been a little bit of stuff done with urban versus rural. The effects aren't easy to sort out because there are a couple of conflicting things. One is that there's at least some evidence that offices tend to warn more in urban areas than they do in rural areas, which would increase false alarms. But you're also a lot less likely to get a report in a rural area than in an urban area, and so it's not completely clear what happens. We do know that performance goes down as you go further away from the radar, and Steve can talk at length about a certain report that was written that should have looked a lot at that. But that basically, as you go from close to the radar to far from the radar in the last several years, that's essentially equivalent to being far away from a weather service radar is essentially equivalent to being early 1990s warning performance on overall national average.
Thank you.
Yep.
You were showing a graph of the probability of detection actually going down the last 5, 6,
Yep.
7 years.
Yep.
What's the reason?
The emphasis on false alarms. Based on the simple decision theory model, we estimated back in 2004 that our current state of performance said that for every point of false alarm that you went down, which is a good thing, you would expect the POD to go down by about 3 points, and that's because it's a rare event, and so what the false alarm ratio from 2008 to 2011, so the beginning of the storm-based era, to after that drops by about 4 to 5 points, and the POD drops by about 14 to 16 points, and so part of that is strictly the emphasis of false alarms. The other smaller part of it is the fact that the warning duration went down. The default warning length went from 45 minutes to 30 minutes, because that's also something that will tend to reduce the POD, because you won't get that warning. In some sense, you won't get the lucky hit that, you had the tornado happen right at the end of the warning. So that was something we did. That was something essentially the system did. Let's emphasize false alarms, and the POD dropped by about, or the fraction of warnings, the fraction of tornadoes warned in advance dropped by 16 points in a matter of 2 years.
Other questions? Anyone online? I have a fun. Scott?
I'll ask a question in the queue.
No, go for it.
Dr. Brooks, thank you for all
Yeah.
your work throughout those years of meteorology and weather science.
Mhm.
Let me ask you, what are you and what are your office and what are some of the projects that NSSL are working on these days?
Well, NSSL is working on a lot of stuff. I'm only involved in tiny bits of it. The big thing that people very near me are working on is more on forecast and trying to use models that ingest radar data all the time, and I'm able to make better forecasts of storm motion, storm behavior out to an hour to 2 hours in advance, trying to deal with there's some sort of interesting, and this is where I come in off to the side of that, is mathematically there's a real difference in behavior between the warning time scale and the watch and longer time scale. And it's a consequence of on the warning time scale, if I tell you there's a tornado very near you, that tells you a lot about the probability that the tornado is going to be at you. When we go onto the watch time scale, our space and time scales are really large. And so, if I've got a watch that's a few hundred miles on the side and 6 hours long, well, the fact that something happened in this watch doesn't necessarily tell me much about what's happening in the next block that's 600 miles by 3. And it turns out you can show some things from some real simple crude models that the behavior is radically different based on how storms are organized. And we're trying to work on that problem. The thing I'm working on right now is we can, at least in theory, and this is not saying it's a good idea, it's probably good for some users, we can issue, we can put out probabilistic information for a lot of the warning. What's the probability that something's going to happen in an event? And we've done some experiments, the probabilistic hazard information experiments, where warning forecasters can come in and say, and draw plumes of probability, and they start off by saying what the probability of a tornado happening is, and then it changes in time. It turns out the way we set up those experiments, some of the improvement we see is basically because we're doing the experiment in a way that the current warnings couldn't fall out of it. And I'm working on some models to try to have those two things happen together, and to be able to hopefully see what the impact of actually being able to, what the impact of doing the probabilities is, as opposed to doing warnings just a completely different way. There's still work going on improving the radars. I mean, we're always, phased array radar hopefully will happen operationally before I retire, but that kind of depends on how long. We get a new lab director. My retirement date may be affected by if I like the new director or not. So that I can't tell you what that time scale is going to be. But that hopefully that will happen. That will allow us to update radar a lot more often. We're doing a lot of work both within the lab and with other components in Norman about how to use information better, because it isn't clear that providing in one sense, providing 1 minute updates on the radar, that may not help warning decision forecasters, because it's just happening so much. And what we actually do see, another one of the little tiny factors of the change in the warning performance, is that there's at least some evidence with this change in the threshold. Part of what happened with that is that as we started putting more radar information out more frequently, forecasters were in some sense, waiting a little bit longer. Let me look at one more radar scan. Because lots of times things would, it fell apart. Well, when you only have radar data every 5 or 6 minutes, you go, I'm not going to learn anything new in the next 5 minutes. I've got to go with what I've got. Instead, I like to think of it as, this Saturday I'll drive from Norman to St. Louis, and the first 100 miles is turnpike with one stop possible, and then I get to Tulsa, and you can stop every mile. Well, if I need to stop somewhere, I have to make the decision on the turnpike before I get to that one stop in the middle, and I'm done for the next 30 minutes. I get into Tulsa and I can decide, well, which QT do I want to stop at? Do I want to stop at the one at Yale or the one thing? Oh, that one over there is not very nice, or there's lots of traffic over there. I'm not going to go. I'll wait till the next one. And so I can wait. And then if heaven forbid, the power is out at the last one in Tulsa, I'm in trouble. And so that's the same thing with the warning problem. I want to look at a little more data. And then if it's already happened, you were late getting the warning out. So I think we're doing a lot of work of trying to figure out how to make useful information, not just information. And that's useful for humans, for forecasters, and for end users. I have a PhD student who's working on expressing SPC convective outlooks not just as the absolute probability that an event will occur in an area, the absolute coverage, but looking at a relative coverage compared to what the climatology is. So that, for instance, the event that we went through last night, this morning, yeah, tornadoes can happen in December in our part of the world, but let's face it, it's not like late April. And, you know, in late April, everybody in the Southern Plains, if you see a thunderstorm, everybody thinks about the possibility of a tornado. You don't think that at, 6 a.m. In the middle of December. And so could we express yesterday's slight risk as this is, 50 times more likely than a normal December day to have a tornado. So we're looking at that also.
Thank you.
Yep.
Where do you see the greatest need to improve in the future here?
I think it's with how users use information. We could stop improving the quality of the forecasts and making the forecast look more like the weather and still get a huge increase in the value of the forecast. Some of this is an issue of how we communicate the forecasts. Some of it is how people have been, for lack of a better word, educated to use the forecast. If you think of the tornado warning problem, a big part of what we depend on is that when we put the warning out, people know what they should do. Because if you have to make that decision about, gosh, where am I supposed to go in the building I'm in right now? And you haven't thought about it before, and it's, we just put the warning out and you're trying to figure out what's the safest room in my building. That's a time pressure that's not easy to deal with. Whereas if you have a really good plan, we put a tornado warning out and you go up, tornado warning, therefore I go here. So how do we get people to make that decision? And some of it is actually, we're actually having some discussions with some of my friends over in the social sciences about, what's the right way to measure the goodness of forecasts in this. And a lot of it is I've started becoming more a fan of some sort of notion of I'm satisfied with the decision I made. Because I recognize that because of whatever my family situation, I couldn't make what you would call a really good decision today. When we did interviews after the May 20th, 2013 tornado in Warren, Oklahoma City, we found a lot of people who made what you might think of as being not good decisions. They went from safe places to dangerous places. Almost every one of those was someone who was going to be in a dangerous place with their family rather than being in a safe place by themselves while their family was in a dangerous place. And yeah, they increased their chances of getting killed or seriously injured, but a lot of emotional needs were satisfied by that decision. So they were happy with that decision. And how do we measure that? How do we measure satisfaction with decisions? Is something that I have some friends who have some ideas, but it's outside of my understanding.
Well, we're getting close to the top of the hour, so I will defer my question to next time I see you in the building.
Okay, yeah, you come on by and we'll try to get the locks changed by then. So
okay. just talk to Sterling. I'm sure he can make it happen.
He can make it out. Yes.
Yeah.
I try not to bring those things up to Sterling because he might do things to me.
So again, thank you so much
You're welcome.
For presenting with us. I will get your address here later on because we have an Amazon gift card for you for presenting with us. So thank you.
Oh, you're welcome.
Yeah. So now for basic chapter business. So again, if you are and want to be a member of the local chapter, $10 are the annual dues, and we get that information to Stanley here. Next month is the AMS annual meeting in Denver. I know I will be there. I'm sure a few of us here will be. It'll be a fun time there, and hopefully, not too wintry. So because of that, it's falling on the second week of January. We will delay the meeting 1 week. I believe that will be the 17th of January. As of right now, we have scheduled Dr. Chris Weiss from Texas Tech University to be our speaker. We'll work on the details of the location. And this will probably be a subsequent meeting between Stanley, Greg, Dave, and myself on this. So other than that, is there any other business we need to attend to? Dave?
I am all good, I think.
All right. So with that, our meeting is adjourned. So thank you all very much.
Thank you, Dr. Brooks.
Thank you.
Thank you.
You're welcome. I enjoyed it. Take care.
Merry Christmas. Oh.
Merry Christmas.
Merry Christmas, everyone.
Yeah, Merry Christmas, everyone.